December 18, 1944. The frozen ridgeline east of Bastogne, Belgium, Oberst Friedrich Müller crouched behind a shattered oak tree as American artillery began its afternoon barrage. He had commanded German artillery for 4 years, understood every sound of modern warfare, knew the difference between incoming mortar fire and howitzer shells by the pitch alone. What he heard that afternoon violated everything he understood about how artillery worked. The shells were not impacting the ground. They were detonating in midair with mechanical precision, 20 to 30 feet above the snow-covered slope, creating a horizontal rain of steel fragments that turned every foxhole, every trench, every defensive position into a killing zone with no protection. Müller watched an entire squad of his men torn apart by shrapnel that seemed to come from above and from all directions simultaneously. These were not random explosions. They were timed with surgical accuracy to maximize casualties. That evening, examining fragments from an unexploded American shell, Müller discovered something that fundamentally challenged his understanding of what was technologically possible. The shell's nose contained what appeared to be a complete miniature radio system, smaller than a wine bottle, packed with glass vacuum tubes each no larger than a thumbnail. These delicate electronic components had somehow survived being fired from a gun at accelerations that should have pulverized them into powder. German engineers had spent a decade concluding that such a device could never be built. The Americans had not only built it, they were manufacturing them by the tens of thousands and firing them as casually as conventional ammunition. This single realization shattered Müller's confidence in German technological superiority and his belief that the Wehrmacht could hold the line through the winter. If American industry could mass-produce technology that German scientists considered impossible, then Germany was facing an enemy whose capabilities exceeded anything High Command had understood or prepared for. The story of how one invention transformed artillery from an imprecise area weapon into a precision instrument of aerial death begins not in the forests of Belgium, but in a series of laboratories across the United States where, in the autumn of 1940, a group of civilian scientists were handed what every major military power had concluded was an unsolvable problem. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The National Defense Research Committee, established in June 1940 under the leadership of Vannevar Bush, brought together America's leading physicists and engineers with a mandate to develop advanced weapons before the United States entered the war that was already consuming Europe and Asia. Among the committee's priorities was solving a problem that had plagued military planners since aircraft first became weapons of war: how to shoot down fast-moving planes when every existing technology required impossible precision or extraordinary luck. Dr. Merle Anthony Tuve, a physicist at the Carnegie Institution's Department of Terrestrial Magnetism, received the assignment in August 1940. Born in South Dakota, educated at the University of Minnesota and Johns Hopkins, Tuve had spent his career studying the ionosphere using radio wave reflection. In 1925, working with Gregory Breit, he had pioneered techniques for measuring how radio waves bounced off the upper atmosphere. This research laid theoretical groundwork for radar. When the committee asked him to develop a proximity fuse for artillery shells, Tuve understood immediately that the same physics might provide the solution. The concept was straightforward: create a fuse that could detect when a shell approached a target, and detonate automatically, eliminating the need for perfectly timed mechanical fuses or impossible direct hits. Simple in theory, seemingly impossible in practice given the brutal reality of artillery forces. When a 5-inch naval gun fires, the shell accelerates from 0 to 2,600 feet per second in roughly 20 feet of gun barrel. This creates acceleration forces of 20,000 times Earth's gravity. Every component inside the shell experiences crushing pressure equivalent to being struck repeatedly by sledgehammers while spinning at 25,000 revolutions per minute. No electronic device in 1940 could survive such forces. Vacuum tubes, the only electronic components available for building radios or amplifiers, were fragile glass envelopes containing delicate filaments and electrodes suspended by thin wires. Standard radio tubes stood 6 inches tall and were designed to sit motionless on a table or inside a radio cabinet. The most rugged tubes manufactured for military applications could withstand 10 times Earth's gravity. The proximity fuse required tubes that could survive 20,000 times Earth's gravity, function perfectly during the few seconds of shell flight, and do so after months of storage in tropical humidity or Arctic cold. The British had explored proximity fuses and shared their research through the TISAD mission when the United States entered the war. British scientists had developed working prototypes using miniature vacuum tubes designed for hearing aids. These prototypes functioned perhaps 50% of the time under ideal laboratory conditions. For military use, this was inadequate. British researchers concluded that while a proximity fuse might work in rockets or bombs, which experienced gentler acceleration, the forces involved in artillery fire made reliable operation impossible with existing technology. Tuve proposed something different. Instead of accepting that the technology couldn't work, he would redesign every component from first principles, specifically to survive artillery forces. He would create a miniature radio transmitter and receiver no larger than a pint milk bottle to fit inside a shell's nose. The transmitter would broadcast radio waves continuously as the shell flew toward its target. When these waves struck an aircraft or reflected off the ground, they would bounce back to a receiver in the same fuse. The frequency of the reflected signal would shift due to the Doppler effect, the same physics that makes a train whistle change pitch as it passes. When the frequency shift reached a predetermined level, indicating the shell was close enough to the target, an electronic circuit would close, sending current to a detonator that would explode the main charge. The project, designated Section T of the National Defense Research Committee, began on August 24, 1940, with Tuve as chairman and a handful of researchers working in cramped laboratories at the Carnegie Institution in Washington. Within months, as the scale of the challenge became clear, the program expanded to what became the Applied Physics Laboratory of Johns Hopkins University, established in March 1942 in a converted Chevrolet garage in Silver Spring, Maryland. Eventually, Section T employed over 1,000 scientists and engineers working on every aspect of fuse development. Their first challenge was the vacuum tubes. James Van Allen, a young physicist who joined the Applied Physics Laboratory in April 1942 as a founding member, faced the task of developing what the team called ruggedized vacuum tubes. He started with miniature tubes that Raytheon and Sylvania had developed for hearing aids, the smallest tubes available in America. These were designed for the gentle environment of sitting in someone's pocket. Van Allen needed tubes that could survive being fired from a gun. Working with engineers at Sylvania Company, Van Allen redesigned the tubes from first principles. The glass envelopes were made thicker and carefully annealed to remove internal stresses. The internal filaments and grids were redesigned with shorter spans and heavier cross-sections to resist breaking under acceleration. The electrodes were mounted more rigidly. Every aspect was tested by firing complete fuses from a vertical test gun into soft earth at the Naval Proving Ground in Dahlgren, Virginia. The soil caught the shells gently enough that researchers could recover the fuses intact and examine the tubes under microscopes to see exactly what had broken. Through hundreds of test firings and thousands of design iterations conducted between late 1940 and mid-1942, the team gradually developed tubes that could survive. By September 1941, they were achieving success rates above 50%. The Navy, desperate for any improvement in anti-aircraft effectiveness against German U-boats and Japanese kamikaze attacks, accepted this failure rate and authorized mass production tooling. The engineers were confident they could improve reliability during the production ramp-up, and they were proven correct. By early 1943, reliability had climbed above 90%, but vacuum tubes were only one challenge among many. The fuse required a power source. Conventional batteries could not survive artillery acceleration. The solution was a specially designed battery using construction techniques that prevented the electrolyte from being forced through the cell separators under high G loads. The battery had to provide sufficient voltage and current to power the radio transmitter and amplifier circuits, remain stable through extreme temperature variations, from tropical heat to sub-zero cold, and function immediately upon firing after potentially months of storage. Western Electric Company developed a reserve battery that solved these requirements. The battery was shipped dry, with the electrolyte separated in a glass ampule. When the shell was fired, acceleration forces crushed the ampule, releasing electrolyte into the battery cells, which activated instantly. This design eliminated concerns about battery shelf life. The fuse could be stored indefinitely and would only activate when fired. Safety mechanisms presented another critical challenge. A fuse containing a live radio transmitter, a power source, and a detonator could not be allowed to arm until safely away from the gun crew. The design incorporated multiple safety features. A mechanical safety pin held the detonator physically disconnected until the shell was loaded into the gun. When the gun fired, centrifugal force from the shell's spin pulled out spring-loaded pins, allowing the electrical circuit to complete. The radio transmitter was designed not to reach operating frequency until the battery had been active for several seconds, ensuring the shell was well away from the ship or gun position before becoming capable of detonation. The detonator mechanism itself required innovation. Conventional artillery detonators used mechanical firing pins driven by springs or small explosive charges. The proximity fuse needed an electrical detonator that would fire reliably from the low voltage and current available from the miniature battery while remaining completely safe during handling and storage. The solution was a hot wire detonator, where electrical current heated a fine wire embedded in a small explosive charge. When the wire reached sufficient temperature, it ignited the explosive, which in turn detonated the shell's main charge. Every component had to be miniaturized. The complete fuse, including transmitter, receiver, amplifier, battery, safety mechanisms, and detonator, had to fit inside a nose cavity approximately 8 inches long and 2 inches in diameter, while leaving room for the shell's 7 pounds of high explosive. Engineers developed three-dimensional circuit layouts where components were stacked and nested with mechanical precision. Wire connections were kept as short as possible to reduce weight and improve reliability. Every unnecessary gram was eliminated. The circuit design itself represented significant innovation. The fuse operated as a continuous wave Doppler radar, transmitting at frequencies between 180 and 220 MHz. This frequency range provided good reflection characteristics from aircraft, while allowing practical antenna design within the space constraints. The receiver circuit amplified the reflected signal and fed it into a discriminator circuit that detected frequency differences between transmitted and received signals. When the Doppler shift reached a predetermined value, indicating the shell was within lethal range of a target, the discriminator closed a relay that sent current to the detonator. The entire electronic circuit had to function with total reliability, using only 3 miniature vacuum tubes and a handful of passive components. There was no room for redundancy. Every component had to work perfectly or the fuse would fail. Testing revealed unexpected challenges. Early prototypes sometimes detonated prematurely due to reflections from the ground, water surface, or even clouds. Engineers developed discrimination circuits that could distinguish between the strong reflection from a solid metal aircraft and the weak reflections from other sources. The fuse was designed to require a certain minimum signal strength before arming, which prevented premature detonation from diffuse reflections while ensuring reliable operation against actual targets. Another challenge was preventing mutual interference when multiple ships fired simultaneously. If dozens of shells with active transmitters were in flight at the same time, their radio signals could interfere with each other, causing premature detonations or failures. The solution was to use slightly different transmission frequencies for different production batches. When a salvo was fired, the shells operated on enough different frequencies that mutual interference was minimized. This approach required careful inventory management to ensure mixed-frequency shells were loaded together, but it proved effective in practice. By mid-1942, Section T had developed a working prototype that met Navy requirements. Reliability exceeded 90% under test conditions. The fuse survived firing from guns, functioned correctly during flight, and detonated at the proper range from targets. The challenge now shifted from development to production. Building a few hundred fuses for testing was one thing. Manufacturing them by the millions was something else entirely. The proximity fuse, designated the Mark 32 for 5-inch naval guns, and later adapted as the Mark 53 for various caliber army artillery, required industrial mobilization on a scale unprecedented for an electronic device. Over 100 factories across the United States participated in production. Sylvania, Raytheon, and Hytron manufactured vacuum tubes. Western Electric produced batteries. Hundreds of smaller suppliers provided resistors, capacitors, and other components. Final assembly occurred at dedicated facilities, where trained workers assembled fuses by hand under strict quality control. Every fuse contained approximately 130 precision components. At peak production in 1945, American industry manufactured 70,000 fuses daily. This required producing 9 million vacuum tubes per month, along with proportional quantities of every other component. The supply chain had to deliver materials from hundreds of sources, all synchronized to keep assembly lines operating at capacity without interruption. Quality control was critical. A single defective component could cause a fuse to fail, wasting not just the fuse itself but the expensive artillery and shell it was supposed to detonate. Every vacuum tube was tested individually before installation. Complete fuses underwent electrical testing before shipment. Random samples from each production batch were test-fired to verify actual performance. The rejection rate was kept below 5% through careful process control and worker training. The cost per fuse dropped from $732 in early 1942 to $18 by 1945, as production techniques improved and economies of scale took effect. Even at $18, a proximity-fused shell cost significantly more than a conventional shell with a simple mechanical time fuse. But the dramatic improvement in effectiveness more than justified the expense. The first combat use of proximity-fused ammunition occurred in January 1943 in the Pacific Theater. The Navy had imposed strict security restrictions. Proximity fuses could only be used over water where there was no risk of unexploded shells falling into enemy hands. If the Japanese or Germans recovered an intact fuse, they could potentially reverse engineer the technology or develop countermeasures. Results exceeded expectations. Anti-aircraft effectiveness improved immediately and dramatically. Gun crews reported that aircraft seemed to explode when shells passed nearby, even without direct hits. Ships that had previously fired hundreds of rounds to damage a single attacking aircraft now achieved kills with salvos of a dozen shells. The psychological effect on Japanese pilots was significant. They reported that American anti-aircraft fire had become uncannily accurate, that ships seemed to predict aircraft movements, that explosions occurred with impossible precision. The European theater deployment began in late 1944, after the Normandy invasion secured continental territory where lost shells could not easily be recovered by German forces. The first use of proximity-fused artillery shells on land occurred during the Battle of the Bulge in December 1944, when American forces used them to devastating effect against German infantry and armor in the Ardennes. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Friedrich Müller, the German artillery commander who had examined that unexploded American shell east of Bastogne, filed a detailed report with his divisional headquarters, describing what he had found. The report made its way up the chain of command to Wehrmacht High Command in Berlin, where German scientists examined it with growing alarm. The technical implications were staggering. If Americans could miniaturize complex radio equipment to fit inside artillery shells and make those systems survive 20,000 G acceleration forces, then American industrial and scientific capabilities exceeded German estimates by orders of magnitude. German engineers had explored proximity fuses extensively between 1930 and 1940, developing over 30 different prototype designs. Some used acoustic sensors that would trigger on aircraft engine noise. Others used electrostatic detectors that would respond to the static electrical charge on aircraft surfaces. Capacitive sensors were tested that would detect changes in electrical field strength near large metal objects. Photoelectric cells were evaluated that would respond to changes in light intensity. Every approach failed to overcome fundamental technical obstacles. The acoustic sensors were too insensitive and unreliable in the turbulent airflow around a spinning shell. Electrostatic detectors required unrealistic proximity to targets. Capacitive sensors lacked sufficient range. Photoelectric systems could not distinguish between clouds, smoke, and actual targets. Most fundamentally, none of these approaches could be miniaturized sufficiently and hardened adequately to survive artillery firing. In 1940, Adolf Hitler's leadership had issued directives prioritizing only those weapons development programs that could reach production within 6 months to support the planned invasion of the Soviet Union. Germany's proximity fuse programs were among the casualties of this strategic decision. Research continued at low priority under Reinhard Borsig, but resources were diverted to projects like jet aircraft and ballistic missiles that promised more dramatic results. By the time German High Command recognized the strategic value of proximity fuses in late 1944, it was far too late to develop equivalent technology. The technical challenges that had defeated German engineers stemmed from fundamental differences in industrial capability and strategic approach. German scientists worked within a system that demanded immediate practical results. Research that might take years to bear fruit was discouraged. American scientists, in contrast, received support for long-term development programs based on theoretical promise rather than guaranteed success. Section T operated for over 2 years before producing combat-ready fuses, a timeline that would have been impossible within the German military-industrial system. More significantly, American industry possessed manufacturing capabilities that Germany could not match. The proximity fuse required precision mass production of miniature components to tolerances measured in thousandths of an inch. American electronics companies had developed these capabilities, producing consumer radios and telephone equipment throughout the 1930s. When war came, this industrial infrastructure could be rapidly converted to military production. Germany lacked equivalent industrial depth. German radio manufacturing remained largely a craft industry, producing relatively small quantities of high-quality equipment. The infrastructure and workforce needed to produce millions of miniature vacuum tubes or precision electronic components simply did not exist. The strategic impact of the proximity fuse on the ground war in Europe became clear during the final months of fighting. American artillery doctrine evolved to take advantage of the new technology. Proximity-fused shells were used extensively for defensive fire missions, where they created aerial bursts that caught attacking infantry in the open with devastating effectiveness. A single well-placed salvo could break up an assault that would have required sustained fire with conventional ammunition. German tactical reports from late 1944 and early 1945 consistently noted the extreme effectiveness of American artillery, using what German soldiers called whispering death, because shells gave no warning before detonating overhead. Traditional artillery impacting the ground produced distinctive sounds as shells approached, giving soldiers fractions of a second to take cover. Proximity-fused shells exploded silently overhead with no warning whatsoever. Medical personnel reported that casualties from proximity-fused artillery showed different wound patterns than conventional artillery casualties. The shrapnel came from directly above, targeting the head, neck, and shoulders. Multiple fragment wounds were common. Soldiers who survived reported that the psychological impact was severe. Traditional artillery allowed some hope of survival through foxholes, trenches, or finding cover behind terrain features. Proximity-fused artillery rendered these protections useless. A shell that exploded 20 feet above a position showered shrapnel downward into foxholes and trenches that would have provided complete protection against ground-burst shells. The sense of helplessness broke German morale in units that faced sustained American artillery fire. Intelligence reports noted that prisoners increasingly cited artillery as the primary reason for surrender, not fear of death, which soldiers accepted as part of combat, but the specific fear of proximity-fused artillery that provided no defense and no way to fight back. This represented psychological warfare at its most effective, accomplished not through propaganda, but through demonstrated futility of resistance. German attempts at countermeasures proved futile. Electronic jamming was theoretically possible, but required understanding the fuse's operating frequency and signal characteristics. Without intact working fuses to analyze, German engineers could not determine the specifications needed for effective jamming. Even if they had developed appropriate jamming equipment, deploying it across every potential target area would have been logistically impossible. Physical countermeasures were equally ineffective. The fuses, operated by detecting radio waves reflected from targets. Reducing the radar cross-section of troops and equipment would have required coating everything with radar-absorbing materials that did not exist in practical form. The human body itself reflected sufficient radio energy to trigger the fuse at close range. The only effective defense was dispersion, spreading forces widely enough that a single shell explosion would not catch multiple soldiers. But dispersion reduced combat effectiveness and made coordinated operations difficult. German tactical doctrine had evolved around concentrated formations that could mass firepower and coordinate movement. Dispersing to counter proximity fuses weakened overall military capability, even as it reduced casualties from any single shell. Units that dispersed became easier to infiltrate and more difficult to command. The cure was nearly as damaging as the disease. By March 1945, as Allied forces prepared to cross the Rhine and advance into Germany proper, proximity-fused ammunition had become standard for all American artillery. Factories were producing fuses faster than they could be shipped to Europe. Forward, supply depots maintained enormous stockpiles. Fire missions that would have been questionable with conventional ammunition became routine. Suspected enemy positions could be saturated. Defensive fire plans could cover vast areas with overlapping patterns of aerial bursts. The psychological effect of this abundance was as significant as the physical effect. German soldiers understood that Americans possessed unlimited quantities of a weapon against which there was no effective defense. This realization, more than any specific battlefield defeat, contributed to the collapse of German resistance in the war's final months. When soldiers believe their enemy has weapons they cannot counter, produced in quantities they cannot match, the will to continue fighting erodes rapidly. The final accounting of the proximity fuse's impact on the European war is difficult to quantify precisely, but substantial evidence suggests it materially shortened the conflict. Military historians estimate that proximity-fused artillery increased the effectiveness of American fire missions by factors ranging from 3 to 5 times compared to conventional ammunition. This meant fewer shells were required to achieve the same effect, which reduced logistical burdens and allowed more aggressive operations. More significantly, the proximity fuse saved Allied lives by increasing the effectiveness of defensive fire against German counterattacks. Positions that might have been overrun by determined assault could be held with fewer defenders when supported by proximity-fused artillery. The mathematical calculation is straightforward. If proximity fuses increased artillery effectiveness threefold, then one artillery battery could accomplish what had previously required 3 batteries. This freed resources for offensive operations while maintaining defensive strength. American forces in Europe fired approximately 22 million proximity-fused shells between December 1944 and May 1945. If these shells were 3 times as effective as conventional ammunition, they accomplished the work of 66 million conventional shells. This represents an enormous multiplication of combat power achieved through technology rather than increased industrial production. The strategic implications extended beyond immediate battlefield effectiveness. Germany had counted on defensive advantages to offset Allied numerical superiority. German tactical doctrine emphasized defense in depth, using terrain and fortifications to multiply the effectiveness of limited forces. Proximity-fused artillery negated many of these advantages. Fortifications that provided protection against ground-burst shells offered no defense against aerial bursts. Troops in the open were equally vulnerable regardless of terrain. This fundamentally altered the strategic calculation. German planners had estimated that defending forces, properly positioned, could inflict casualties at ratios of 3 or 4 to 1 against attacking forces. These estimates assumed conventional weapons operating within historical norms of effectiveness. Proximity-fused artillery changed those norms. Defensive positions became less tenable, counterattacks became more costly. The mathematics of attrition shifted decisively in favor of forces equipped with the new technology. Friedrich Müller survived the Battle of the Bulge and surrendered to American forces in April 1945 as German resistance collapsed in Western Germany. In post-war interviews conducted by American intelligence officers, he consistently identified proximity-fused artillery as the weapon that had the greatest psychological impact on German soldiers, not because it was particularly destructive compared to other weapons, but because it demonstrated comprehensive technological superiority in a way that destroyed confidence in ultimate German victory. Müller explained that German soldiers had been trained to believe that German engineering and German science were superior to anything the Allies could produce. This belief sustained morale even as Germany suffered reverses. The proximity fuse shattered that belief comprehensively. It was not just a clever weapon. It was a miniaturized radio system, mass-produced in quantities that seemed impossible. It represented capabilities that German industry could not match, and German science had declared impossible. When soldiers examined proximity fuses that failed to detonate, when they held in their hands devices containing dozens of miniature vacuum tubes that had survived being fired from guns, when they understood that Americans were producing hundreds of thousands of these devices monthly, the psychological impact was devastating. It proved that America possessed industrial and scientific capabilities that exceeded German understanding. If Americans could do this, what else could they do? What other technologies might they deploy? The questions undermined confidence and hastened the collapse of resistance. The proximity fuse's legacy extended far beyond World War II into the development of modern weapons and electronics. The miniaturization techniques pioneered by Section T influenced the entire electronics industry. The necessity of fitting complex circuits into tiny spaces drove innovations in component design and circuit layout that became standard practice. The transistor revolution of the 1950s, built directly on knowledge developed making proximity fuses work. The quality control methods established for proximity fuse production became models for manufacturing industries beyond electronics. The concept that every component must be tested, that statistical process control must be applied rigorously, that workers must be trained to precise standards, these principles were proven at scale in proximity fuse factories. Post-war American manufacturing excellence owed substantial debt to lessons learned, producing 22 million fuses under intense time pressure with zero tolerance for failure. The workforce training programs demonstrated that complex technical work could be performed by people without advanced education, given proper instruction and supervision. Many workers in proximity fuse assembly facilities were women with no previous electronics experience. They were trained to perform intricate assembly tasks, wire delicate circuits, and test completed units to exacting standards. This proved that technical capability was not limited to a small elite, but could be distributed widely through effective training programs. These lessons shaped post-war American industrial development. The scientists and engineers who worked on proximity fuses went on to distinguished careers that shaped the second half of the 20th century. James Van Allen, who had developed ruggedized vacuum tubes, became one of the founding figures of space science. The Van Allen radiation belts surrounding Earth were discovered by instruments he designed. Merle Tuve returned to the Carnegie Institution and continued leading scientific research. Dozens of other Section T personnel joined universities, industrial laboratories, and government research facilities, bringing expertise in miniaturization, electronics, and systems engineering that established American leadership in technology. The intellectual capital developed during the proximity fuse program helped create the scientific and industrial foundation for the Cold War. Missile guidance systems relied on miniaturized electronics hardened against high-G acceleration, direct descendants of proximity fuse technology. Satellite systems required compact, reliable electronics that could function in extreme environments. Nuclear weapon fusing mechanisms applied principles developed for conventional artillery. The entire trajectory of post-war military technology traced back through the proximity fuse to those initial efforts in 1940 when Section T began trying to solve what everyone else thought was an impossible problem. The industrial infrastructure created for fuse production found new purposes after the war ended. Factories that had manufactured vacuum tubes converted to producing television tubes and consumer electronics. Workers trained in precision assembly became the workforce for the emerging electronics industry. Supply chains established for fuse components supported the growth of consumer electronics markets that exploded in the 1950s and 60s. The story of the proximity fuse ultimately reveals fundamental differences in how nations approached technological warfare. Germany invested heavily in advanced weapons like jet aircraft, ballistic missiles, and heavy tanks. These were impressive engineering achievements that promised dramatic capabilities, but they came too late and in too few numbers to affect the war's outcome. Germany sought war-winning superweapons that might offset Allied numerical superiority through technological superiority. America took a different approach. American scientists and military planners sought effective weapons that could be mass-produced immediately. Proximity fuses, while sophisticated, were designed from the start for mass production. Every decision in their development prioritized manufacturability and reliability. The result was a weapon available in overwhelming numbers when needed. Not perfect, not revolutionary in dramatic ways, but very good and available by the millions. This reflected fundamental differences in strategic thinking. Germany's approach to technology was rooted in craft traditions, where individual items were made to the highest possible standard. America's approach was rooted in industrial mass production, where adequate quality produced in vast quantities overwhelmed superior quality available in limited numbers. The proximity fuse embodied this philosophy perfectly. It was sophisticated enough to work reliably. It was simple, enough to manufacture by the millions. It was effective enough to change battlefield outcomes. It was available in sufficient quantities that it could be used without restriction. The result was decisive. By early 1945, American forces possessed not just superior numbers, but superior technology deployed at superior scale. German soldiers faced an enemy who could produce impossible devices in impossible quantities and deploy them as casually as conventional ammunition. This combination of technological sophistication and industrial mass production proved unstoppable. The proximity fuse stands as testament to what free societies can achieve when they combine scientific excellence with industrial might and unwavering determination. It proved that sometimes the greatest victories come not from seeking the impossible, but from making the necessary possible through sustained effort and adequate resources. It demonstrated that innovation without production is merely interesting, while production without innovation is merely adequate. Only the combination of both achieves decisive advantage. German soldiers who survived the war and faced proximity-fused artillery consistently described it not merely as a weapon, but as a demonstration of comprehensive superiority. They understood implicitly that any nation capable of miniaturizing radio transmitters, hardening delicate vacuum tubes, and manufacturing the results by the millions possessed capabilities beyond their ability to match or counter. The proximity fuse ended their war not through any single dramatic defeat, but through accumulated weight of countless engagements, each proving the same lesson. They were fighting an enemy whose science was more advanced, whose industry was more capable, whose resources were more abundant, and whose will was more determined than anything they could oppose. That realization, more than any battlefield loss, broke the Wehrmacht's spirit and hastened the Third Reich's collapse. The shells that seemed impossible to build became the shells that changed warfare and helped decide the largest conflict in human history. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.